So in this video, we're going to talk about ERC1155 action and the first kind of the role it plays in the overall Notional protocol, and then we'll go through the code and kind of explain how it works. So ERC1155 is a token standard. It is coined as the multi-token standard or something of that effect. And what it allows for is a single contract to represent many different tokens that are sort of identified by a 256-bit ID. And this is convenient for us in Notional because we can have any number of Fcash assets sort of transferable behind a single contract interface. And when we think about Fcash, typically if you think about other tokens that are represented as ERC20s, so for example like CDAI and Compound, there's one sort of CDAI asset for the DAI currency within Compound, right? So it's 1-to-1, and CDAI sort of never matures. It's sort of like always giving you some variable rate of yield, and that's quite nice to model as an ERC20. Now for DAI in Notional, we may have FDAI at 1 month, at 2 months, at any number of dates in the future, and that becomes very unwieldy to model as ERC20 if each one of those maturities needs to be an individual ERC20 token, right? Then you just have many different contracts, and it doesn't scale very well. So ERC1155 makes this a lot easier for us. There's going to be one contract always that users can interact with to transfer Fcash assets and liquidity token assets, and they will be identified by sort of an ID. So we'll take a look at the ID. As we discussed, it's defined by currency ID. So that's going to be one per currency type that we support, and maturity, which is going to be an arbitrary date in the future, and asset types. So Fcash will have an asset type of 1, and then the different individual liquidity tokens will have other sort of incrementing asset types. So when we talk about liquidity tokens in this context, we're talking about actual liquidity tokens in an individual Fcash market. nTokens are going to be ERC20 tokens, so nDAI, nETH, all of those are actually modeled as ERC20 tokens. They are transferable just like any other ERC20 token. So what we're really talking about here, practically speaking, is going to be Fcash transfers. Now we'll look at some of the kind of more mundane aspects of ERC1155 here first. So the first is balance of, pretty straightforward. The main thing to note here and to be very careful of is Fcash is a signed integer. You can have a positive or negative value of Fcash. Now the ERC1155 standard specifies that this should return a uint 256. It does not. And so as developer, you need to be really careful about that. The second thing we'll talk about is approvals. So in ERC1155, we have the notion of operators who are allowed to sort of take action via the ERC1155 contract. And we have 2 levels of approval in Notional. So one, we have an account level approval. So an account can authorize any particular operator to transfer Fcash on their behalf. And the second type is a global transfer operator. So governors may set an operator, may allow an operator to transfer Fcash for all users. This would largely be like a convenience thing for users, so that they don't have to go all individually set approvals. So for example, we may enable another protocol which has off-chain order books to be a global transfer operator for everyone. So that would maybe be like a Kyber protocol or 0x. And the reasoning for that is that what ERC1155 enables via safe transfer from is the ability to trade Fcash OTC. or over the counter. And what that means, practically speaking, is that as Notional extends maturities out further and further, from the 1 year to the 2 year to the 5 year, what that's going to practically mean for users is that there will be periods of time where their Fcash will not be tradable in on-chain Fcash markets, in on-chain liquidity pools. So, for example, even with the 1 year Fcash asset, if you lend for 1 year, at the end of the quarter, when that 1 year loan, that 1 year Fcash asset now is 9 months away, so after 90 days, that particular Fcash market that it was trading in will be settled and reinstantiated 90 days in the future. So now what that means is your 9-month Fcash asset does not have a matching on-chain Fcash market to trade with. So if you're to hold that Fcash asset to maturity, you have no problems. You will get what you're owed. But if you want to exit that Fcash position, if you want to sell it off and get cash for it today, there will not be a corresponding on-chain market to actually sell it off. So what we want to do is enable users to be able to exit those positions, and we can do that via market makers. So what market makers can do is take possession of your Fcash. You can transfer it to them, and in return, they will transfer you corresponding amount of USDC tokens. And those types of trades are possible through things like 0x or Kyber, where there's an off-chain order book, and you can sort of execute those transfers on-chain. And so what we're looking at with Safe Transfer from would be the Fcash leg of that kind of two legs of the trade. The Fcash leg, and then there's going to be some sort of ERC20 token transfer, which we don't handle within this contract. So looking at Safe Transfer from, we're going to validate the accounts. This is simply just checking that these are valid addresses, and we're also going to check approvals if the sender is not the same as the from address. So we're just kind of checking authorization. Part of the ERC1155 spec, which I think is quite nice, is that if the destination account here is the 2 is a contract, what we're going to do is ensure that that it will actually accept these Fcash assets. And one place that we actually use this is in nTokens. So nTokens will not accept any Fcash that you try to transfer to them. And this is important because we want the nToken to kind of like sort of be a very controlled environment, and nothing unexpected should happen to it. So that's a quite nice feature of the ERC1155 spec, is this requirement, which we do make use of. So when we're transferring a single asset here, it's quite simple. We decode the asset ID that has been provided to us. We decode the amount, and we check that this is actually a valid cash asset that we can transfer. And then we'll go ahead and transfer it. So when we transfer here, the way this works is that we will place the asset in the to account. So we'll place if the amount is 100, we will place 100 Fcash in the destination account, and then what we'll do is we'll invert the notional, so we'll flip the sign, and we will place negative 100 Fcash in the from account. Now, if the from account has 100 Fcash, they'll simply go down to 0, and and that transfer will take place. Now, if the from account has no Fcash, they'll actually incur a negative balance, so they'll now incur a debt of 100 Fcash. And what they will, in either case, what was in effect happening is that, the to context is sort of borrowing from the from context. The to account is borrowing from the from account. And so this is quite nice because what it allows for is a market maker to essentially create debt by just simply transferring Fcash to another account. And so that account can sort of lend to the market maker. The to account can lend to the market maker by getting positive Fcash. The market maker receives negative Fcash, and the to account can also transfer back to the market maker some amount of cash. And so this is the crux of an OTC trade. These two parties are going to agree to exchange cash for Fcash, and they'll likely do that at a sort of exchange rate and interest rate ratio that reflects what they could do on chain. And so this is sort of really kind of nifty little method here. The other thing that we allow in safe batch transfer from is the ability to do a bidirectional transfer. So when we look at this decode to assets method again, we'll see that even though here in the batch transfer we're specifying that amounts are uint256, we actually decode it as an int256. So we're not really concerned about this kind of like causing clashes, because Fcash doesn't really use the entire uint256 numerical space. So this should be okay. And what this allows you to do is sort of swap Fcash assets. So for example, if a user has a 9-month Fcash asset that is, like as we discussed, not liquid in any Fcash market, and they want to exchange that for a 1-year Fcash asset that maybe is liquid on chain, what they can do is trade with the market maker. So they will give the market maker the 9-month Fcash asset, and the market maker will give them some amount of 1-year Fcash asset, which is liquid on chain, and they'll be able to do this through safe batch transfer from, since the transfers are going in 2 different directions. So someone's getting positive and someone's getting negative on either side. Now, the last thing we have here is a post-transfer event. So in the ERC1155 spec, you are allowed to specify arbitrary, call data. And so market makers can use this to execute a trade on the notional liquidity pools or redeem nTokens as inside a single transaction. So what we'll do here is we will take a look at this call data. If it does match one of these method signatures, we will decode the address. So the first parameter of all of these methods is going to be an address that of the account that is transacting. We'll check the authorization of that transaction here, and then we're going to go ahead and call it. Within this call, it will check free collateral for either account, so we don't recheck it here if the transacted account is equal to the to or the from. And then for the to account, we generally would not check free collateral, since we know in most cases they're going to be receiving Fcash, positive amount of Fcash, so that's similar to a deposit. Their free collateral balance will always go up. We don't need to check it. However, if we're transferring negative, they'll be losing Fcash, and we do check a free collateral. We do check their free collateral at this point. So that concludes how ERC1155 action works. So now I'll talk about the nToken redeem action. So nToken redeem is done when a user wants to convert their nToken balance back into the underlying. So if you're providing liquidity via nDAI and you want to get your DAI back out, this is the method that'll be called. So there are 2 external methods on this contract. There's the nToken redeem via batch. So this method is called via batch action only, and it does not allow residuals to remain after redeeming. So we'll talk about what that means. And then there is another external method that users can call directly. And and it can also be called via ERC1155 action. But what occurs here is that you can redeem your tokens, and you can optionally tell the contract whether or not it should try to sell any residual amounts. So the key thing to note about redeeming nTokens is that if there are these Fcash residuals as a result of providing liquidity, the account has two options. One is to receive that Fcash into their portfolio, or the other option is to sell those net Fcash positions off back into the Fcash markets. Generally, we think most people will want to sell them off back into the Fcash markets so they get the max amount of cash back out, and they don't have these sort of residual Fcash positions that are likely going to be fairly small and just clutter up their portfolio and sort of be dust amounts. So generally, users will be using nToken redeem via batch, which will just attempt to sell off all those residual positions. But it's possible that in certain scenarios, there will be residuals, there will be idiosyncratic residuals that cannot be sold. And so nToken redeem is a way for accounts to sort of get around that and still redeem their tokens. Perhaps they can still attempt to sell most of the residuals, but leave the idiosyncratic residual in their portfolio if they really need to get their cash out. So this presents sort of an option that will always work to some extent. So we'll take a look at this method really quickly. So we'll get the account context, we'll load the balance, we'll ensure that the nToken balance is sufficient, and then we'll call redeem. And this is largely what happens in this method as well. So within redeem, this method is fairly straightforward. What we're going to do is we're going to reduce the token assets of the nToken proportionally to the tokens that are being redeemed. And then if we're selling the token assets, we're going to loop through them and try to trade them on the Fcash markets. And then we'll finalize all the market storage states. So when we reduce the token assets proportionally, one thing you can't do is in this window of time when the nToken needs to be settled, you can't redeem at all. This will fail. But again, anyone can call initialize markets, and there's a strong incentive to ensure that initialize markets is called very quickly. So this amount of time should be quite short. What we'll do is we'll reduce the Fcash assets proportionally. This code is not too sophisticated. It really just loops through all the Fcash assets and loads it, determines what the proportional amount is, and then returns an array of these Fcash assets that need to go back into the account. Now, it's possible that the nToken balance, the nToken also has a cash balance, so we'll ensure that the user will get a share of that. And then here we will remove the liquidity tokens. So removing liquidity tokens is, again, fairly straightforward. We're going to loop through it. We're going to update both the market position and the position of the nToken. Now there's an edge case where where the net sort of Fcash position is like exactly 0. This is highly unlikely, so what we're going to do is simply fail on this. If this does happen, any bit of lending on that particular maturity on that particular Fcash market will move the residual off of the 0, like off of exactly 0, and redeeming would be okay again. But this is like quite the edge case, but we do need to sort of deal with this to ensure that we don't we don't improperly set these Fcache assets in memory. The last thing here, another edge case that can potentially happen, is that that redeeming these nTokens somehow eliminates the number of reduces the number of liquidity tokens in the nToken portfolio. So this would happen if one particular liquidity token was reduced down to essentially 0. And in this case, we will fail as well. So this is just to say that we sort of expect a liquidity token to be in each Fcache market, sort of mark their positions. We sort of rely on that logic in other places. So if this does occur, we will fail. Now the user can still redeem the vast majority of the value, but they'll have to leave behind some dust amount to mark that position. And then we'll finally look at selling Fcache assets. So, you can look at this loop carefully. What is happening here is that we're going to loop through all the Fcache assets, and we're going to skip any Fcache assets that are sort of idiosyncratic, that don't match the market's maturity that is currently being traded. And what we'll do is we'll trade the negative version of the Fcache asset. So if we have a positive amount of Fcache, we're going to borrow and receive some amount of cash in return, and the result will be 0 Fcache in the portfolio. So that after selling those assets, we'll sort of have this total amount of asset cash, total amount of C tokens that the account will receive, and that's what will occur here. And finally, if the account has debt, we do make sure that we check free collateral and revert here. So in this video, we're going to talk about the nToken incentive emission rate. So this is set by governors, and the governors will set a target emission rate for a year, denominated in whole tokens. So stripping off the 8 decimal portion of note governance tokens. And what this emission rate represents is sort of a target number of note tokens that will be minted to a particular currency, and the nToken holders that have been providing liquidity over a set period of time. So this is sort of an annualized target annualized rate for emissions. Now, nToken holders will receive incentives based on what the average total supply of nTokens has been over the time that they have been providing liquidity. So, we know that the total supply of nTokens is going to fluctuate as users mint and redeem nTokens throughout the year. And so with this incentive emission rate, it's just not going to be as precise as we can be with Fcache. It's sort of a target rate, and we may mint more or less incentives than this, but it should be fairly close. With the balance handler, this is what will trigger claiming of incentives. So in the balance handler, when we see that nTokens have been transferred, or there's a net nToken supply change, which will be the result of minting or redeeming nTokens, we will claim incentives for the account. The reason for this is that the numerator for the incentive calculation is going to be the account's nToken balance. And so what we want to do is ensure that we are always claiming incentives on the correct balance. So every time it changes, we ensure that we mint incentives. So now when the other place users can claim incentives is manually. So they can call this function, and it will sort of manually claim incentives over for that user at that point in When we look at the claim incentives method, what we will get here is the first thing we'll do is change the nToken supply. So we'll take a look at what this method does. So when we change the nToken supply, what we'll do is calculate this thing called the integral total supply. And when you can think of the integral total supply is it's sort of the numerator within a weighted average of the kind of weighted average total supply. So one way to kind of see this is to look at the definition of a weighted average. So in a weighted average, the weight in our case will be the period of time that a particular total supply amount was valid. It was the actual total supply, and X will be the total supply. And so the integral total supply is going to be this numerator, this summation here, sort of a running total for like all time. And then the denominator is going to be sort of like the elapsed time for for this weighted average. So looking at what we have here, we have the previous integral total supply, and now we're going to add to it the value of the total supply that was valid previous to this particular change, and how long that total supply was the actual current value. Now, if the supply is actually going to change, what we will do is go ahead and change the total supply and save off the integral total supply that was valid up into this point. So it does not include this new total supply value. And what we'll use that integral total supply to then calculate the incentives that a user should receive. So we get the incentive rate, which is sort of the pro rata years that since the last time this particular user claimed incentives, and then what is the emission rate over that year. So ensuring that we are in the correct denomination here. Now the average total supply is going to be the current integral total supply minus the last time, whatever the integral supply was the last time this user claimed, and the time since that last claim. So that, and then we kind of take their balance, multiply the incentive rate divided by the average total supply. So at that point, we will transfer those incentives to the user, and we'll set the current time as the new last claim time, and we'll set the integral total supply as well. Now, one thing we do want to note here is that we're always looking for gas efficiency within Notional. So when we go ahead and set the balance storage, we want to fit this within a single 32-byte storage word. Now, with cache balance and nToken balance, we want to maintain sort of exact precision, so we don't do this, and same thing with the last claim time. However, we only really have 56 bits left inside this storage slot, which is not really sufficient to store the full accurate integral supply value. So what we'll do here is pack it into 56 bits using sort of this floating point type compression. So what this does is if the value is greater than uint48, which is sort of 1 byte less than what we have available, we're going to get the most significant bit and we're going to shift it down. We're going to shift that value down such that we only retain the 48 most significant bits of that integral total supply. So we're going to lose some precision. We're basically going to truncate down, anything that's less significant than those 48 bits. And when we unpack from that, we're going to take the bit shift, which we store in the smallest byte of this 56 bits, and we're going to shift that value over. So we're essentially truncating off sort of the least significant parts of that integral total supply. Now, what that's going to result in is some loss of precision here, likely in favor of the person who's claiming incentives. But we think this is kind of worth a little bit of storage efficiency, and it shouldn't change the ultimate value too much. So that is claiming incentives.